I've said hello to everyone in the room already and everyone on Zoom. This hello is for you watching online in the future. It's semester 2, 2022, hello from the past. And here we are doing a revision seminar for Maths 1A. Okay, I'm going to start with some of this stuff on matrices first and then move on to some other things. I don't know what to title it. It is called matrix stuff now. Okay. So, can I just check? The person who said matrix, was there anything in particular? No? Okay. All good. So, matrices are a handy place to hold numbers. That's like an Excel spreadsheet, really. And they just hold numbers. But the reason why mathematicians are so interested in them is that for two things. One is that you can set up addition and multiplication in a really interesting and mathematically satisfying way. And the other one is you can use them to do stuff that people want to do. So before matrices were invented, people had to do everything with linear equations with x's flying everywhere. And once matrices were invented, things were just a little easier. And then once computers were invented, matrices became really useful. So the reason why we have matrices as such a huge part of maths now is more or less because computers were invented. Before that, mathematicians used to say, anything you can do with a matrix, I could do without a matrix, but now everyone's like on board with matrices. So the really important thing to know about matrices is how matrix multiplication works. So just a second. Whenever you learn about any new mathematical object, you should know what it is and how to write it, what things you can say about it, and how to do operations on it. So if you have ever learned about complex numbers, you go, this is what a complex number is, these are the different ways of representing complex numbers, here's how to draw them, here's how to convert between the representations, here's how to do multiplication and addition. You do all of those things so that you know how it works, and that's what we need to do with matrices as well. So our matrices can have any numbers in them at all. Technically, you could even have irrational numbers. There's nothing stopping it. Having like a root 5 in there is a perfectly good matrix. And it's a rectangle. And it has, these things are rows, and these things are columns, and you say how many rows and how many columns it has by saying this matrix has size, and sometimes people call it order 2 by 3. It has 2 entries here, there's 2 numbers in each column, that's what the 2 stands for, and there's 3 numbers in each row, that's what the 3 stands for. So it's 2 this way, and it's 3 this way. Now, I say all this just in case a person who watches this in the future hasn't seen all of this already. And the last thing to know is that the actual individual numbers are called entries. That's an entry. Cool. And this entry here is the entry in row 1, position 3. So that's entry 1, 3. And this entry here is the entry in row 2, position 2. And so the rows are numbered from the top down and the columns are numbered from the left to the right. And you say which row you're in and then which position within the row. That's how you define where you are in a matrix. Okay, cool. And that's, not particularly satisfying, it's whatever. But the point is that I can treat matrices as mathematical objects in their own right, and do operations on them. So this is what matrices are. So sometimes you say a matrix has size 2 by 3 or order 2 by 3, or you say that just the matrix is 2 by 3. And you never multiply those two numbers, even though if you multiplied it would tell you how many entries there were total, but it's just read aloud as 2 by 3. All right, cool. That's the very, very basics. And matrix multiplication is the most important thing to know about. But I'll do matrix addition first. So matrix addition, your matrix has to match up in sizes. And you add the matching positions. So 2 plus minus 1 is 1, 3 plus minus 3 is 0, 5 plus 0 is 0, 0 plus 5 is 5. So yeah, I caught myself. 1 minus 2 is negative 1, and 7 plus 8 is 15. We just add the matching positions. That's exactly how vectors work. When you add vectors together, you add the matching positions as well. So they're not different from vectors in that way. Oh, that's supposed to be a 5. Is that what you're saying? Yep, good move. Thank you. Never trust a pure mathematician with actual numbers. So, okay. So you add the matching positions. And just like with numbers, where I could call a number X or A or W or theta, I can call a matrix by a letter, and I can have a letter to represent the entire matrix as a whole. So I might say something like A plus B equals C, something like that. And it's traditional to use capital letters for matrices. You can use a small letter for a matrix, but people will be confused if you do. But it is technically possible. There are no rules, there are just vibes with choosing letters for things. Okay, so matrix multiplication is a whole other thing. Okay, matrix multiplication is designed to do two jobs simultaneously, and I'm going to show you both of the jobs with an example. That is not how I wanted to write it. I'm skipping ahead. So the first kind of matrix multiplication I want to show you is if you have a matrix made of a single column multiplied by a matrix made of a single row. And when you multiply a matrix made of a single column by a matrix made of a single row, you get a grid of products. So in my head, I'm thinking there's a 3 and a 5 here, and there's a 10 and a 2 and a minus 1. That's what I'm thinking. And 3 times 10 is 30, and 3 times 2 is 6, and 3 times minus 1 is minus 3, and 5 times 10 is 50, and 5 times 2 is 10, and 5 times minus 1 is minus 5. So if you do a single column by a single row, you get a grid of all of the products of each number in one multiplied by each number in the other, and then just make a grid. That's the first thing to know about matrix multiplication. How do people feel about that? And that's totally a thing that you want to do sometimes, to multiply all of these numbers by all of these numbers. Like these are prices, and these are how many you sold, not with a negative, but whatever. And you want to know what the cost was of everything. So that's one. And the other thing that matrix multiplication does is the other way around, is to have a single row by a single column. So if you do a single row by a single column, the way the process works is that you multiply the matching positions and you add them up. And so what you end up with is a single number, 30 plus 10, which is 40, minus 1, so 39. So you get a sum of products. And there are reasons why mathematicians chose to do it this way, and I don't feel like going into it, and sometimes I can't remember what they are. But this is more like saying, well, this is a list of prices and this is a list of so maybe this is a list of amounts of things sold and this is profits and losses, and each one has to go with each one, you add them up. So these are the two things that matrix multiplication is designed to do. So if you have a single column by a single row, you can make a grid of any size you want. It doesn't matter how big, how long these are, they can be different lengths. But if you have a single row and a single column, they have to have the same number of entries or you're not going to be able to do this thing. If this one has more than this, then the one doesn't have anything to go with and you can't actually do the process. So have to be the same number of entries in each. And those are the two things that matrix multiplication are designed to do. And if you want to have a matrix that's bigger than either of those things, you have to do both of those things simultaneously. So either okay, so if it had just been the first row and the first, can I do this? We haven't got enough fingers. The first row and the first column, that would produce a sum of products. This times this plus this times this. So let me show you something. Let me do it in rows and columns. Okay. Look back in the distance of what I'm looking at here. And pretend those things are numbers. I have a column and a row, which makes a grid. So I have to make a grid of the things I get from doing the other thing. So I have to make a grid of sums of products. Yeah. So I'm going to have to go, if I was making a grid, I would imagine this, right? And I would imagine this. And in these positions, I would put the answers of this one times this one, and this one times this one, and this one times this one in the matching spots in the grid. So I'm going to put 1 and 2, 3 and 4, 10 and 1, 20 and 0, 8 and 5, and this one times that one goes in this spot, and this one times that one goes in this spot, and this one times that one goes in this spot. Most people don't draw this, but some people find it really useful. Most people just follow their fingers along as they do the matrix multiplication. So I can say 1 times 10 plus 2 times 1 is 12. 1 times 20 plus 2 times 0 is 20. 1 times 8 plus 2 times 5 is 18. And 3 times 10 is 30 plus 4 is 34. 3 times 20 is 60 plus 0 is still 60. And 3 times 8 is 24 plus 20 is 44. So there you go. How are people feeling about that? Good, good, good. I want to show you the other way of multiplying matrices just because it's really cool. What if I saw it this way instead? And saw these as columns and these as rows? Then I would be going along here and down here, just like I do with this. And so I will make a sum of products. I'm going to get 1, 3, to go with 10, 20, and 8, and 2, 4 to go with 105. And that would give me two grids. This grid is 10, 28, and 30, 60, 24. And this grid is 2, 0, 10, and 4, 0, 20. And then I add the matching spots, and I've got 12, and 20, and 18, and 34, and 60, and 44, which is the same answer. Isn't that cool? I think it's cool. Yeah. But wait, there's more. Or let me just do one of them and show you what happens. When you multiply a matrix by a single column, you're going to need there to be the same number of entries here as there are here. And multiplying a matrix by a single column is going to produce 10 of the first column and 1 of the second column. You just hear them shushing each other. Very, very pleasant. Proud of them. So watch how this works. If I do this in the first way to do multiplication, it'll be that row times this column. And so the 1 will get multiplied by 10 and the 2 will get multiplied by 1. And this row times this column, the 3 will get multiplied by 10 and the 4 will get multiplied by 1. Well, so these first two both get multiplied by 10. And these second two both get multiplied by 1. And so when you multiply a matrix by a column, what it does is say this many of that column and this many of that column. And what this is called is a linear combination of columns. The reason I'm doing this, one of the reasons why mathematicians love matrices is they're so flexible and you can think about them in lots of different ways. It's one of the reasons why mathematicians love fractions as well. Because they're so useful, because they can be thought about in so many different ways, they are useful for so many different things. But I will say one more thing, this works the other way around as well. If you have a row, then you can think of this as rows as well, and have this of the first row, and this of the second row, and this of the third row. So it'll be 5 of 1, 1, 2, plus 1 of 0, 8, 9, plus 7 of 2, 2, 10. I just put commas in when it's a single row, otherwise it's hard to see where one number ends and the next one begins. So putting a row on the left-hand side will combine these rows together by having some number of each of them and produce a new row. And it only requires this to have the same number of entries as this. Okay. That's matrix multiplication. Just wait a moment, just trying to think. But wait, there's more. Ready? Oh, this one's even cooler. I'm favouring 1s and 2s today by the look of it. Are you ready? I could see this as a matrix and this as a matrix. And this would be the same answer as now a grid that has 1, 0, 2, 2 here and 5, 8, 0, 7, 1, 3, 2, 5. So these are two entries that are both matrices. So I can do that as well. I can totally break a matrix up into pieces and multiply it by another matrix made of pieces and make a new matrix which has the matrix AE plus the matrix BF, which is exactly what I would do if they were numbers, and the matrix CE plus the matrix DF. And this is a new big matrix made of two smaller matrices. Like, you can break your matrix up in as many different ways as you want. As long as all the sizes match up for multiplying and everything, it'll just work, which is just fabulous. I love it so much. Okay, matrix multiplication. I'm going to stop waxing lyrical about matrix multiplication, but I will say that these two things are one of the reasons why matrices are so useful for helping think about vectors. Because a vector is a list of coordinates. And so this is a vector, these two are column vectors, these two are row vectors. Because matrix multiplication automatically encodes linear combinations of vectors, and linear combinations is exactly what mathematicians think vectors are for, matrices are useful to help with vectors because they talk about linear combinations. I can say all this at this end of the course because you've now heard of all these words. If I said it at the beginning, it might not be so useful. Okay, cool. So one last thing, there are two special matrices. There is the identity, and I say the identity, there's a different identity for every size. They have to be square, and they have ones down the diagonal and zeros everywhere else. They can be as big as you want. They're called identity matrices, and they're all called I. So if you think the person reading your work is going to know how big your identity matrix is supposed to be without you telling them, you can just call it I. Otherwise, you can explicitly say this is the I with 2 entries per row and column, this is the I with 3 entries per row and column, this is the I with 4 entries per row and column, and so on. And it's off the page because I wanted it to look like the thing continued. But if you don't want to tell someone how big it is and just want them to figure it out from context, you can just call it I. That's the identity matrix. And the identity matrix has the pleasant and useful property that if you multiply it by any other matrix on one side or the other, you get the same matrix back again. It's called the identity because if I said, I'm thinking of a matrix, you tell me a matrix to multiply it by, and I'll tell you the answer, and then you have to guess what my matrix I'm thinking of is. And so that's okay, I multiply it by the correct size identity. And then that will just give you what the matrix is. It's called the identity matrix because it reveals the identity of your matrix, of your other matrix. Yeah. Thank you to a student last semester who came up with this idea. It's beautiful and I love it. That's why it's called that, for this reason of why it's called the identity. Okay, well, that's the identity matrix. And the other matrix is O, which is the zero matrix. It's the letter O. Okay, just really important, it's not the number 0, it's the letter O. Though I will say some mathematicians also write it as the number 0. I find that confusing. How do you know if a 0 is a matrix or a number? So the letter O is usually traditionally used for the 0 matrix, and the 0 matrix can be any size you like. It doesn't even have to be square. It just has to be filled entirely with zeros. And the 0 matrix has the same property that number 0 does, that A plus the correct size 0 matrix to be able to do the addition will be A. And A times the correct size matrix to do the multiplication will be O. But it is technically possible for this O to not be the same as this O, depending on how big A is. Because, you know, that will be the same size. Damn it, David, what are you doing? That will produce a 3 by 3 O. So this O is a different O from that O, just so you know. And if you really want to specify which one is which, this is an O 2 by 3, and this is an O 2 by 2, and this is an O 4 by 3. You can say how big it is if you want. But most people will just write this and you'll just go, that's okay, I'm okay with it. This O is different from that O. Which I think is awesome, because most of the time mathematicians are really uncomfortable with one letter representing two things in the same equation. But when they're doing this, they just go, whatever. And I just think it's funny. So that's what they are, and I just therefore wanted to do one last matrix multiplication example. The same one I did before, but with matrices that are helpful. This times this is 2579, and this times this is 0000, and I can cut it into the pieces without having to do all the multiplication individually. That's where this is called a block matrix, by the way. And it'll work. So yeah, cool. All right. So the other thing one can do with matrices is row operations. And the reason one would want to do row operations is because it matches with what matrices were invented for, which was holding information about systems of linear equations. That's what matrices were first invented for. So just as an aside, something like that is a system of linear equations. And what I could do is I could wrap that up inside some vectors. Like that. I'm just doing several steps. Normally you do this only in one step. Saying that this number is equal to 8 and this number is equal to 15 is the same as saying the first coordinate of this is the same as the first coordinate of this, the second coordinate of this is the same as the second coordinate of this. And then this is a list of, this is a sum of products, and a sum of products happens when you multiply a row by a column. And this is also a sum of products. It's 1x and minus 1y and no z's. And so you can represent your system of equations as a matrix equation, which makes people happy. Now, notice a couple of things here. The number of columns here is, number of entries in this column is the same as the number of entries in this column. So it's technically okay for me to just think of these as two things that line up together. And the x, y, z is keeping track. This is 3 x's and 2 y's and 5 z's back in the original thing here. But it's also, you could think of it as, we can now start saying, well, this is the same as x lots of the vector 3, 1, and y lots of the vector 2, minus 1. But z lots of the vector 5, 0 is the vector 8, 15. That's a different way of me thinking about it, because that's one of the things that matrix multiplication does. It does that. It says this many of that vector and this many of that vector and this many of that vector. And so now, because of matrix multiplication, system of linear equations is connected to linear combinations of vectors. Because of matrices, they're connected together now. Okay. Right. So, the things that you would used to do before matrices were invented, like back in the 1850s, the things people used to do to solve linear equations, and we still do them today, would be things like multiplying the second one by 2 and adding them together so that the y's cancel out, for example. And those sorts of operations on equations translate into operations on the rows of this matrix. And so row operations started life as things to do to a matrix because we remember that the matrix belonged to a system of linear equations. But then they took on a life of their own because they became so frelling useful. And what I want to say is that row operations I'm going to call them elementary row operations. Started out life as things to do with equations. They started out as equation operations. And they are of these types. So your new row 2, for example, is this like 5 times your old row 2, something where you multiply a row by a number. You're not allowed to multiply a row by 0, that's bad. Not 0 times row 2, not allowed to do that. And your new row 3 and row 4 is the old row 4 and row 3. Some people write this as row 3 switches with row 4. That's another way of saying it. And your new row 3 is like the old row 3 plus 7 of row 1, something like that. And you are allowed to put a 0 in this spot, but what that means is that the new row 3 is the same as the old row 3 and you actually haven't done anything, but you're allowed to not do anything. You're always allowed to do nothing. Not if you want to get anywhere, but you can do it if you want, just to say, I just need a break for a couple of seconds. I'm going to do this empty row operation just because I just need a moment. So that can be 0, but this can't be 0. So these are the 3 types of elementary row operations. And in your book, they'll normally be written with an I instead of a 2 because they don't want to specify it's row 2. It could be row anything. I for index is what it stands for. And I just want to point something important about this is that in this row operation, the row that you're putting the new row into is the same as the row it came from to begin with. We don't do 7 row 1 minus row 3. That is not an elementary row operation. It is still a perfectly good row operation, it's just not an elementary row operation. Because the row 3 appears in its answer as minus row 3. To be an elementary row operation, the row 3 that you're adding to has to appear in the answer as the original row 3 unchanged with another row added onto it. So this here, 7 row 1 minus row 3, is not an elementary row operation because it's technically doing 2 things simultaneously. It's minusing row 3 and adding 7 of row 1. So those of you who have learned row operations before or from the internet, you're going to have to unlearn this row operation for the purposes of Maths 1A. Sorry. It still will progress you to the answer, but it's not an elementary row operation. Yes? Yep, 2 steps. It would have to be row 3 is minus row 3, and then row 3 is row 3 plus 7 of row 1. Yep. Okay. But we were so excited about matrix multiplication, like, well, I was. I was so excited about matrix multiplication, and row operations are a weird-ass thing to do if you think about matrices as objects that are like numbers that you do addition and multiplication for. What if there was a way of representing row operations with matrix multiplication? And there is. Yay. Ready? Ready? It's so cool. Watch this. See this thing here, row 3 plus 7 of row 1? That's a linear combination of the rows. And so that would happen if I did 1 of row 3 and none of row 2 and 7 of row 1 times row 1 and the matrix made of row 1 and row 2 and row 3. That would produce this exact linear combination, 7 of this one and none of this one and 1 of this one. How cool is that? That's so cool. And so if I want a matrix that has this in the 3rd row, so this is 7 of row 1 plus 0 of row 2 plus 1 of row 3. If I wanted that in the 3rd row, I'd put this in the 3rd row so it ended up as the 3rd row. And then I want the 1st row to be the same as the old 1st row, so I'll have 1 of row 1 and none of row 2 and none of row 3 in the 1st row. And none of row 1 and 1 of row 2 and none of row 3 in the 2nd row. And that will do my row operation for me, multiplying by this matrix. This matrix is called an elementary matrix because when you multiply on the left, it does the row operation. Cool. If you wanted to do column operations, you'd put a matrix on the other side, because to get a linear combination of the columns, you need to put a column on the right-hand side. But we don't do column operations, but just to let you know, it's a possibility. Yeah. There you go. But this is the thing that when I realized it, I was the most excited about in maths, the whole of Maths 1A that month. So I tend to get excited about Maths 1A. It's my favourite of the first year maths courses. Maths 1B is fine. It's all Maths 1B is much better connected than Maths 1A. Everything fits together a bit nicer, and it does have cool things in it, but Maths 1A is still my favourite. So I have, in my talk about matrices, happened to talk about elementary matrices in a different place than they were in the lecture, but only because it felt right to me to try and do row operations as matrix multiplication. Yeah. And so in my head, that's their only purpose, just sitting there being cool. That's what they're for, just like, isn't this cool? Their real purpose is to prove that the process of finding the matrix inverse works. So one last step, there is one more thing, inverses. So if they're going to be numbers, they're like number-like objects, I can add them, I can multiply them, I can definitely subtract them, that's fine. I can multiply an entire matrix by a number. What if I could divide them? And the answer is, you ridiculous person, why would you be able to divide them? We can't divide them, but some matrices we can nearly divide. So some matrices, let's call them A, have an inverse called A inverse, A to the power of -1, which is not the same as 1 over A. Don't be ridiculous. so that A times A inverse is I, and A inverse times A is also I. And the only way to do that, the only way for two matrices to be able to multiply in both directions is for them to be the same size and one of them to be the other side, one of them to be the transpose size of the other. And so this will only going to work if A is square as opposed to properly rectangular. So some of them have an inverse. If it's not square, it doesn't have an inverse. If it's not square, it may possibly have one matrix that goes on one side to make it come out to the identity, but there won't be one on the other if it's not square. It'll only work on one side, not the other. And if it is square, if it has one that works on one side, it will work on the other as well. So technically the definition says that it has to work on both sides to come out to the identity, but it only has to work on one and it'll be guaranteed to work on the other, actually. There's like a theorem that says that. And it's really nice if you do have them, but you do have to keep very careful track of the order your matrices are in. Because if you have something like A times X equals B, and you want to figure out what X is, you could multiply both parts of this equation by A inverse, but you have to make sure that they're both on the left-hand side or both on the right-hand side. And you can't multiply on the right-hand side. You can, it just doesn't tell you anything because the A inverse is not next to the A, and so I can't tell what's going to work out to be. It really matters which order matrix multiplication is done in, and you get a different answer if you do it in a different order. So there is absolutely no guarantee that this will work out to X. But this will, because A inverse times A is the identity, and I times X is X. So be really careful when you multiply matrices on both parts of an equation. It has to be on the same side of both parts of the equation. And that's why when I talk about doing things to both parts of an equation, I don't say both sides. Because when I'm doing matrices, I have to do it on the left-hand side of both sides and I just get confused. So that's why I say parts. Also, if you're doing inequalities, sometimes there's three parts simultaneously and there's not like three sides. That doesn't make sense. So. And the way to find an inverse is to secretly use elementary matrices. And sometimes in this course, explicitly use elementary matrices. So here's the thing. If I have a matrix and I do row operations and I get the identity, then that guarantees that A will have an inverse. If it doesn't have an inverse, when I row reduce it, it will not produce the identity, it will produce something else. It will be impossible to produce the identity if this doesn't have an inverse. And if you do row operations, each one of those row operations is multiplying by a matrix on the left-hand side. And so it'll be row operations, you know, row operation 1, 2, 3, 4, 5, and each one of them will have an elementary matrix to go with it. And what this means that if to do the first row operation, I'll multiply by E1 on this side, and that'll give me an answer. And then I'll do the second row operation. Even better, I'm going to be even more explicit about this. So here's my row operations. So I do row operation 1, and I'll get, the answer will be E1 times A. And then I'll do row operation 2, and the answer will be E2 times whatever I had last time. And I'll do row operation 3, and the answer will be E3 times whatever I had last time, which was E2, E1, EA. And you'll keep going until you get to the identity. And once you get to this point, I produce the identity. Row 4, row up 5. And look, this matrix times A produces the identity, which therefore means that this matrix must be A inverse. Because that's what an A inverse does. When you multiply A inverse by A, you get the identity, and it's the only matrix that does that. And so this proves that when you multiply all these elementary matrices together, you get the identity, you get the inverse, and it proves that the inverse really exists if you can row reduce to the identity. But it also proves something nice, which is if they started with I and did this row operation, that would be E1 times I. And then if I did the next row operation, that would be E2 times E1 times I. And that would be E3 times E2 times E1 times I, and so on. And I would get, at the bottom here, E5, E4, E3, E2, E1 times I, which is the same as E5, E4, E3, E2, E1, because the I doesn't make a difference. And therefore, this thing here is A inverse. Because that's what happens when you do all those matrix multiplications. You get the same list of things, but the things they're multiplied by is the identity, which means it's just that thing. So what this proves, elementary matrices are capable of proving. This doesn't usually count as a proof. You would have to put lots more words in. But this proves that the process of starting with A and I and row reducing until this side becomes the identity will mean that by the time you get there, this will be the inverse. And this is the gold standard way of finding matrix inverses. Yep. There is a different way of finding matrix inverses. If you Google finding matrix inverses, about half the time, someone will tell you about the cofactor matrix and the adjoint, which is not in Maths 1A anymore. It used to be in Maths 1A. Yep, the adjoint has in every position the little piece of the determinant you would get. Yep, yeah. Yep, I'm not going to go into it, but you can talk to me about it. I love adjoints as well. Right, and so that's that. It is a really cool process. This is the standard way of finding it. You can do it via cofactors and the adjoint matrix, but don't. A, because it's not, that cofactors and adjoints not in this course, and B, it just takes longer. Like for a 2x2 matrix, shorter. 4x4 matrix, longer. Yep?
Why are matrix inverses important?
Matrix inverses are important for two reasons. One is for solving equations like this, where you have matrix times something equals other matrix. But you don't actually solve these equations like this, you just do row operations. So, and they are important because mathematicians love inverses. Inverses are cool. Like from an algebra point of view, like a real algebra point of view, where algebra means the structure of things that are like numbers, it's just really cool that matrices have inverses. Numbers have inverses, and so do matrices. That's just nice. They're from a mathematician's point of view, of really cool theoretical importance. And you can't get away from it just being related to other stuff. Like, it's much easier to say matrix A has an inverse than it is to say matrix A row reduces to the identity. And so it's just an easier thing to talk about. And you can use them in proofs. Mathematicians love proofs. So from a usefulness for solving actual problems you want to use matrices to solve with, not useful. But from a how is everything in matrices connected to each other, interesting. Yeah. And this course has to service both purposes because it's for everyone, both people who are using maths and people who are making maths in the future. So we have to do them both. Yep. Yeah, 2 to the power of -1 is 1/2, but it's also the multiplication inverse of 2.
So why is that a to the power of -1?
because numbers do have division already before we define what negative to power of -1 meant. So, but matrices didn't have division already, and you can't define division in a way that makes sense because the multiplication isn't always in the same order. So, yeah. And every number except one number you can do division, but most matrices you can't do division. And so we don't want to imply that that division is a thing that works for all matrices, so we just don't say it.
Is that number 0?
Yes, that number is 0. You can't divide by 0 because there is no way of consistently deciding an answer for that problem. As Cookie Monster says, if you ask Siri what 0 divided by 0 is, if you try and share 0 cookies between 0 friends, what does that even mean? And Cookie Monster is sad because there's no cookies, and you are sad because you have no friends. That's what Siri says if you ask her what 0 divided by 0 is. I don't know if she still does, but that's what she used to about a couple of years ago. You should try it. You see, what that means is that the people who design, the people who work at Apple have all done a maths course and have all watched Sesame Street. So, okay. So, that little aside, I'm almost up to, that's cool. So that's matrices. And I would recommend being good at matrix multiplication and being good at seeing matrix multiplication in multiple different ways. Every time they try and prove something using matrices, they will use a different flavor of how matrix multiplication works. So Maths 1B is full of that stuff. They'll go, oh, today we're seeing it as linear combinations of vectors, or today we're seeing it as linear combinations of row vectors, and today we're seeing it as every row, this whole matrix times this column, and this whole matrix times this column, and this whole matrix times this column. And you'll have to be able to move with that and allow yourself to see it in all those different ways. Okay, so cool. But they do very much. I think I've actually done this. Okay. They do very much solve linear equations. They definitely do solve linear equations. And it's really important to know that linear equations have solutions. This linear equation here that I wrote, this pair of linear equations, doesn't have enough information to tell you what x and y and z are. There's only 2 equations and there's 3 unknowns. I can't tell what all 3 of x, y, and z are specifically from this equation. There'll be lots of different options. In fact, there will be infinitely many different options, or possibly none. That's a possibility as well. So what will happen when you try and solve differential equations, not differential, damn it, sorry, I did Maths 1B yesterday, they did differential equations, linear equations. What will happen when you try and solve linear equations is that you will either get one solution, or no solutions, or infinitely many. And your infinitely many solutions comes in several different flavors. Some infinite solutions are bigger than other ones because they have more ways to do them. And so and this process of infinitely many 0 or 1 solutions, this was all decided long before matrices existed. Like back in the 1820s and the 1850s, people knew all about there being infinitely many solutions and no solutions and whatever. And they studied it before matrices were invented. But now we have matrices, it's a little easier to do the calculations. I'm famous for saying, not famous, but I do say very often that Lewis Carroll, the writer of Alice in Wonderland, was a mathematician and his research area was linear equations and determinants. And so that's how old it is. Alice in Wonderland was written in 1860s, and it's been around for that, but matrices were only sort of invented in the 1910s. So, right. Possibly earlier, before World War I, but after Alice in Wonderland was published, somewhere in there. Okay, so I can solve linear equations using matrices. And I can use row operations to do it because that's the quickest way. And so when I try to solve linear equations with matrices, I take my coefficients and I turn them into, so you have equations and they've got like x1s and numbers. Looks like that. And then you'll turn it into a matrix and you'll take all the coefficients and you'll join them together into what they call an augmented matrix, meaning that this matrix is the coefficients that came from what I made earlier, this thing here. Not that one. This thing. And this little column is these answers, which is this thing here, and I glue them together like this. And the only reason to glue them together like that is so that your row operations affect them at the same time. Now, a computer, like Desmos for example, cannot see this line. You can't put it in there. And so you're just going to have to, when you enter this thing into a computer, pretend that it's there. Only you, the human being, can see that. So it's not really there. This is really just one big matrix. But I'm remembering that it was made by gluing two smaller matrices together. And then what you do is you do row operations. And you go as far as you need to decide the answer you want to decide. But most people go all the way to the reduced row echelon form. But you do not have to go that far. So if some decisions you want to make, you don't have to go all the way to the end to be able to tell what the answer is. So I just want to point that out. You don't have to go all the way to the reduced row echelon form every time. And the reduced row echelon form looks like this. There may be a column of zeros at the beginning, several columns of zeros, but somewhere after that, there will be the first column of the identity matrix. And then there may be columns after this, and then sometime after that, there will be the second column of the identity matrix. And sometime after that, there will be the third column of the identity matrix, and so on. That's what it will do. It will continue that way. And before this one, the only thing that's allowed to be in this spot is columns made entirely of zeros. And the only thing that's allowed to be in this spot is any number here, but the rest of them have to be zeros. And you can have any numbers in these spots, but the rest of them have to be zeros. That's what a reduced row echelon form looks like. The word echelon is French for staircase. Well, Latin for staircase, basically. And so this is the staircase, see? Like that. Possibly ladder, but staircase works better in this context. When's I'm supposed to finish? Did I start at 11:30? Yeah, so 1:30. Okay, cool, I've got time. I just had this horrifying feeling that the next revision seminar was supposed to be coming in and I was over time, which means two things. One is I'm over time and two, I've missed lunch. So, all right. So most people describe the reduced row echelon form based on the rows. It's useful to know that when you come in from the left, every row starts with zeros until it has a 1 as the first entry, and then all the rest of them can be whatever you want. And every one of these leading ones, they're called, is when you go down the rows, the leading ones are further to the right. But I actually really prefer to think about it in columns. It's got the columns of the identity in the correct order. You may not have all the columns of the identity that you can fit, but they're in the correct order inside this matrix. And between them, it looks like you just have to have the same number of zeros, same position zeros as the column before it, basically, in between. Yeah. And the reason I focus on that is that those columns that end up with the identity matrix columns in them are the really important ones to focus your attention on. So some people call this leading one a pivot as well, for reasons that I'm not 100% sure, but you know, maybe that's where you turn I guess when you're coming down the staircase, you turn from down to across at that spot, but maybe. I don't know. It's just called a pivot. Pivot is also a verb. The action of pivoting is producing one of these ones and the zeros above and below it. That is what the action of pivoting is. So to pivot is to make one of these columns. Yep. All right. Best with an example. So this is not technically in reduced row echelon form, because if it was in reduced row echelon form, there would be a 1 in this position here. But this bit's in reduced row echelon form. So have a look at this. I can see the first column of the identity there, and the second column of the identity there, and the third column of the identity there. And I didn't get to the fourth column of the identity before I left the original coefficient side of the matrix. And if this was a system of linear equations, these would all go with the number x1, and these would all go with the number x2. Okay. Tell me something you notice about this. You tell me it doesn't have a solution. Does everyone agree? Lots of people agree. Why? Someone who isn't you, why does it not have a solution? So you're saying there's a row of zeros here, and this isn't 0. So it's because this is a row of zeros and that is not 0. If this was 0, I'd be okay. And it's not because, so the thing is, it's not that these numbers have to add up to 0, have to add up to this number. It's that this number times x1, and this number times x2, and this number times x3, and this number times x4, and this number times x5, and this number times x6, and this number times x7, they all have to add up to 8. And there are no possible choices for x1 to x7 that will do that, because if I do 0 times all of them, the answer is going to be 0. But it's totally okay for this to say 1 and 7, because it's 1 times whatever x7 is 7. And so is there a choice for x7 that makes that work? Yes, the answer is 7 for x7, which is a coincidence. I'm going to change this to a different number just to be absolutely sure that we know that it's not always the number, that position that it's in. Okay, so this one has no solution because of the 0 rows. And this is not 0. So if at any point in your working, whether you've gotten to the reduced row echelon form or not, you get a full row of zeros and something in the last column that is not 0, you can stop and say, there's no solutions. You don't have to get all the way to the reduced row echelon form to tell there's no solutions. The moment this happens, you can stop. Yep. Does not even have to be in the last row. It can be anywhere. If you're in reduced row echelon form, it will be the last row. But it could have happened in an earlier row somewhere in your working, and that would be okay. So it could even have been here and there'd still be no solutions. Still no solutions, even though it's in the middle row, because you have 0, 0, 0, and 10, and that's not 0. All right. Anyone want to notice anything else about this matrix? I have one in mind, so I really shouldn't ask a question like this. It's bad practice as a teacher to ask questions where you have something in mind and hope that students guess what it is. So I'm just going to tell you, this column of zeros means that the number x1 isn't actually in any of these equations. I'll have 0x1 and 1x2 and so on. None of these equations actually have x1 in them. So why would I even put x1 as a column in this matrix? And it's because maybe there's a variable in my mind that goes with the situation I'm thinking about. So there are situations where you go, oh, well, I need to know how much flour and how much water and how much milk and how many eggs and whatever to make this thing. And it may turn out that your profit is completely unrelated to how many eggs you have, because it doesn't appear in any of the equations. It's totally possible for that to happen, to have a variable that you're thinking of that you wrote down but didn't appear in the equations. And I warn you, in Maths 1B, this will happen in a different situation again. There will be columns of zeros that happened along the way, and you need to know that. Okay, so what if it was this? So that's the first rule. The first rule is you look for rows of zeros and look to see if the answer at the end is zero or not zero. And if it's zero, fine. If it's not zero, no solutions. And if it's zero, well, fine, and you still haven't made a decision about how many solutions there are. But the only way to get no solutions is for this to appear somewhere. That's the first thing. And I think that neatly answers that bit, not all of it. So the other thing that can happen so this matrix is okay. This system of equations is fine. It does have a solution because the row of zeros does come out to zero. If there's no rows of zeros at all, it'll have a solution. That's fine too. And when I look for my, yep?
What if there's not enough information to solve the equation because no row of zeros?
Yep, cool. I'm just going to make a matrix exactly like that. That's like that. Still has a solution. At least one, because infinitely many is more than one. And so it still counts as at least one. Yeah. Okay, so let's look at these. This one's got the first column of the identity here and the second column of the identity here, and that's as many as I have. This one's got the first column here and the second column here and the third column here, and that's as many as there can possibly be. I can't have any more because it's only got 3 rows. It's because not every column is one of those pivot columns, there must be infinitely many solutions. And that's the decision. After you've dealt with there being a solution or not with your rows of zeros, then look to see where your pivot columns are. And if they don't cover all the columns, then there are infinitely many solutions. Please don't say infinite solutions. It's infinitely many solutions. All of the solutions are finite. None of them are infinite. The number of solutions is infinite. So you say infinitely many. Because if you're not going to use proper grammar, then the world will go to pot. Yep. Ah, well, that's a worth thing. That means that the columns are linearly dependent. Please avoid using the word it in maths, if you can. You have to say explicitly what the it is, so that people know what you mean. Because these rows are linearly independent. So don't just say it's independent or it's dependent. Not that you were wrong, you were completely right. I knew what you were thinking. Yeah, but you can't trust that the person reading your exam knows what you're thinking. So be explicit about it. I did. I know. The columns are linearly dependent, the rows are linearly independent. This matrix, the columns are linearly dependent, but the rows are linearly, the columns are linearly dependent, but the rows of this matrix are linearly independent. Yep.
What does it mean for the columns to be linearly dependent?
I'm going to come back to that. So if I forget in the next 15 minutes, please ask again. Okay. That everyone else can hold me to that. Yep. Yep, there is not a pivot in every column, so the columns are not independent. Yep, they are dependent. Right, I'll get back to linear independence in a minute. Okay, so last one, maybe second last one. This matrix, this will have one solution, and mathematicians normally use the word a unique solution. Now, I haven't gotten it all the way to the end of my reduced row echelon form, but I can still tell that there will be a unique solution from this information here. So if I did the reduced row echelon form, it would come out to this. I don't know what's going to be in this spot when I get there. So because every column has a pivot, there's a unique solution. But I can tell that it's going to get to this spot because this is already in the staircase form. This is called echelon form, row echelon form, as opposed to reduced row echelon form. So I can tell that I could put zeros above this and that would work. And then at that point I could put zeros above this and that would work. And then I could put a 1 here and that would work. I can tell there's going to be pivots in these positions. And so I can tell from this information there will be a pivot in every column. And so therefore it will have a unique solution. So that's what I was saying, you don't have to get all the way to reduced row echelon form to tell that. Yes?
That question, the one that you just did, would you put that here out? Would you put that in reduced row echelon to solve it?
Yeah, so to solve it, yes, you would have to put it in reduced row echelon form.
Couldn't you just get the value of x? Like
yeah, so you're saying that you could go, well, x3 is 6, and I'll sub that in here and figure out this one, and then I'll sub that in here and figure out this one. Yes, you can do that. Yeah, so that's going back to the original linear equations that they represent. And you can do that, but it's quicker and easier to go to reduced row echelon form, because that does the same job. Yep. It's easiest to tell that way. So if I just had a random matrix, it would be hard to tell whether there's going to be pivots or not. I have to get it to this point to know for sure. Is that what you're asking?
Yeah, so it's like, as you just said right away about what you know.
Yeah. A lower triangular matrix will do it too. So if I had zeros at the top, same thing would happen. That'd be okay as well. And I'm sure there is a combination of zeros at one end and, yeah, but I don't, too hard to tell. So the easiest way to tell is to put half of the matrix zeros and then you'll be able to know. But yeah, so good point. Could have been up here and that would have been okay as well. It is tradition to put zeros below, just because. I don't know why. So I like to think of alternate reality maths and like, what if we lived in a reality where we put the zeros at the top? No one would notice most of the time. So talk to me one day about the reality where fractions are written the other way up. So where a half has a 2 at the top and a 1 at the bottom. That's a fun one. And the integral of ln x is x over 1. No. Someone's going to take that as out of my seminar and say that I said that. That's okay. So that's how to tell. The way to tell how many solutions there are is to first check for rows of zeros, and then you'll know whether there's solutions at all. And then if there either aren't any rows of zeros or all the rows of zeros have a 0 at the end, then you can see where the pivots are. And if every column has a pivot, then there's a unique solution. But I'm going to say one more thing. This is still a unique solution. It doesn't matter how many rows of zeros there are. That doesn't make any difference to whether it's a unique solution or not, other than preventing there from being pivots in places. So because there is a pivot column in both columns, it's a unique solution. The rows of zeros are irrelevant to that. Yep?
Just in regards to the no solution,
Mm-hmm.
you're saying if at any point while you're reducing a matrix, at any point if there's a row of zeros.
With that the end isn't 0.
The end.
Yeah. So you need a row of zeros where the number in the answers column is not 0.
Yeah, that can happen at any stage.
Any stage. If it's right at the beginning, you can just say straight up without doing anything, there are no solutions. It wouldn't be, because that would be that your original equation was 0 equals 10. But usually at least one step away from the original equations. Yeah, but it could happen at any point. Okay, so just want to point out, the unique solution is this, that the first variable, this equation is 1x1 and 0x2 is 3, and this equation is 1x1 and no x1s and 1x2 is 5, and so the unique solution is that x1 is 3 and x2 is 5. That's the unique solution. There is only one option for what both x1 and x2 can be. And when we talk about solutions, we talk about them as a combination of the x's. So there is only one combination of x1 and x2 together which answers these equations at the same time. So we can talk about it as the vector is the vector 3, 5, if we want. The reason I'm saying that is just because x1 is 3 doesn't mean that it's a unique solution. It could be that in some situations you have x1 is 3 and x2 is 7, and another combination is x1 is 3 and x2 is -4. It's okay to have repeated answers in different ones, but the combination is different. Yeah. So they are the only options. You cannot have exactly 2 solutions to a system of linear equations. You can have no solutions, or exactly 1 solution, or infinitely many. If you've got 2 solutions, there must be infinitely many solutions. Yep. The difference between unique and at least 1 is that unique means there's exactly 1, and at least 1 means there could be 1 or there could be infinitely many. So at least 1 solution means 1 solution or infinitely many solutions. But it doesn't tell you which is which. It just says at least 1 solution means I'm in one of these 2 situations, but I haven't told you which one. It just means there's not no solutions. Yeah. Okay. Now, in some places, when you first learn about solving systems of linear equations, if you get infinitely many, you just stop and say there's infinitely many. But in this course, you don't stop and say there's infinitely many. You say there are infinitely many, and here is the list of all of the infinitely many solutions that there are. That is what we're going to do. Because it's not like everything is a solution. There's still only some of the solutions are solutions. It's just that there's infinitely many of those some. Mathematicians have a very flexible definition of some. It just means not none. So, right, so actual example now. I don't want a 0 there. Will I put numbers at the end? Yes, I will. I'm going to make it easy for myself and make this number 16 and this number 6. Okay. So here's my list of equations. It says 3x1 and 5x2 and 8x3 add up to 16, and 1x1 and 2x2s and 3x3s adds up to 6. It is a coincidence. So the fact that 3 plus 5 plus 8 equals 16 and 1 plus 2 plus 3 equals 6 means that actually if I made x1 the number 1 and x2 the number 1 and x3 the number 1, it would work. So I do already have one solution. So it can't have none because there is one. I think there's more. There have to be infinitely many because I don't have enough information to figure out what all three of x1 and x2 and x3 are because I've only got 2 equations. So I would do row 1 is and row 3 swap. There's only 2 rows, David. And that would put my 1 in the right spot. And I would do row 2 is row 2 minus 3 of row 1. So I need a 0 here. In my head, I'm imagining the first column of the identity. That's what I'm trying to make. And I've made the 1, and now I need to make the 0. And the way to make zeros is to do row operations like this, where you subtract one row from another. That's how you make zeros. You can't make zeros in any other way than that. You can't multiply by 0, and you can't swap rows to make a 0. I mean, you can, but that would destroy a 0 that's somewhere else. So I now have, I didn't change row 1, but this minus 3 of that is 0. 5 minus 3 of minus 3 of 2 is 5 minus 6, which is negative 1. 8 minus 3 times 3 would be 8 minus 9, which is also negative 1. And 16 minus 3 times 6 would be 16 minus 18, which is negative 2. And so I've got my second column of the identity now, and so now I'm aiming for this. So I need a 1 in this spot. I can't now get a 1 from anywhere else because that would destroy the 0 I've just made. So I can only start using rows that are further down from here. And so I'm going to do my new row 2 is minus the old row 2. That will put a 1 in the right spot. And then I will do my new row 1 is the old row 1 minus 2 of row 2. And that'll put a 0 in this spot. Didn't change row 2. 1 minus 2 times 0 is still 1. That's the whole point. We try not to break our ones that we've made. 2 minus 2 times 1 is 0. 3 minus 2 times 1 is 1. 6 minus 2 times 2 is 2. And so here I am. I have got my 2 columns of the identity. I can't fit any more columns of the identity because I've run out of rows. And so that's as far as I can go. It is now in reduced row echelon form. And I can tell from this information that x1 plus x3 is 2, and x2 plus x3 is also 2. So here are my columns of the identity. They're my pivot columns. The columns that don't have those in them are non-pivot columns, and the variables that go with those columns are free variables. And when we say free, it means it's free to be any number it wants. You know how you say things like, let x be 5? Letters are waiting around to be things. and then you let them be stuff, and they go, yes, I get to be something today. This one is free to be whatever it wants to be. You don't tell it what to be, it chooses what it wants to be. So x3 is free. So I could just call it x3, but then I don't feel like I've done anything. And so what I do is I write that x3 is called t. For t, any number in R. And that seems like a waste of everybody's time because I have a letter and now I've called it a different letter, but at least I feel like I've done something. Never underestimate the importance of feeling like of feelings in maths. Like a lot of the things we do in maths are just because it makes us feel better. So x3 is t. And now that x3 is t, I have enough information to figure out what x1 and x2 are. So from the first equation, from the first row, I have that 1x1 plus 1x3 is 2, but x3 is really t. Okay, I put a let there. And so x1 is 2 minus t. And from the second row, no x1s and 1x2 and 1x3 is 2, but x3 is really t. And so I've got x2 is 2 minus t as well. It's very rare that they come out to be the same thing. And so now if I collect them together, x1 and x2 and x3 is x1 was 2 minus t, and x2 was also 2 minus t, and x3 was t. And they're all the solutions. Every vector that looks like this is a solution. Every combination of x1, 2, and x3 that are related in this way is a solution. And it's tradition to split this up into a vector with just the numbers and a vector with the t's. And to split it up one step further than that into this. Like that. Yep. I just heard the beginning of that. The 2 to 0 is at a point.
Through the line T with 1.
Okay. So the answer to what you're saying, to what you're thinking is yes, but it's not the answer to what you said. So the point 220, let me just step back a bit. If I coloured in all of the points with these coordinates in a 3D graph, it would be a line. And the point 220 would be one of the points on that line. Yes. And the direction that that line faces will be the vector -1, -1, 1. Yep. Ah, cool. Awesome. Thank you. Remind me again in a second. Yeah. Yeah, you're going to say something.
Is this column vectors or what does that mean?
I explicitly wrote them as column vectors because of this. So, and also it was easier to fit everything in and writing it as a column. If you've got a formula in this spot. So technically when you do matrices for linear equations, the vectors are column vectors, but nobody really cares. Unless they started out telling you it was a column vector and then you have to have a column vector. But traditionally, to write that matrix equation, it has to be a column. Yeah. But I just find it easier to fit everything if I write it as a column. But it is okay to write it as a row as well. That's all right too. Mathematicians are pretty flexible about whether it's rows or columns, unless you actually have to multiply it by a matrix, and then if it's on the right-hand side, it has to be a column. Like you can't put a column vector on this side of a matrix because the sizes don't match up. Yeah. But almost always, whether they write them as rows or columns, whether it's written as rows or columns is not relevant unless you want to write it as matrix multiplication, and then it has to be a column. That's the answer. Okay. Does that answer the question about this thing? Okay, cool. So I will say one more thing. Sometimes you get more than one free variable. In this case, there was only one. Sometimes there's two. And when you get two free variables, what it makes is a plane and not a line. And planes are bigger than lines. You know how I said there's sizes of infinitely many? Well, there's lines, that's infinitely many. There's planes, that's infinitely many, but that's more than the infinite many that the lines have. In the sense of dimension, in a whole other sense, they're the same size, but don't get me started on that. So that's a hotel infinity sort of thing. So this is a line through the point 220. But it also has the point 002 on it as well, because this plus 2 of that is one of the answers, and 002 works. If you go all the way back to your original equations, 2 of this is that. And so 0 of this vector and 0 of this vector plus 2 of that vector is this vector. That's another one of the solutions. And every possible way of thinking of combining these columns to produce this is covered in this. But what this is none of the actual rows or columns in this matrix are represented here. What these represent are the coefficients that go in these spots. No, coefficients of the vectors or the variables that go in those spots. These numbers aren't part of this matrix. Yeah, that's important. All right. Take a breather, process, sharpen my pencil, let you all think for a bit. Okay. How are we feeling? I'm glad to have talked about this because as much as I know there are people in the room that I have talked about this before, sometimes you need it again, and sometimes you get through the whole of Maths 1A just feeling, like you can do it, but you don't get it. Or almost like you could possibly maybe do it, but you're afraid of getting it wrong. And it's a terrible feeling to have a couple of weeks or less out from the exam. So I'm glad to have talked about it. Okay. One of the major purposes of the Maths Learning Centre is to make people feel better about their mathematics. And about their place in it. So I'm hoping that some people are feeling better about that. Okay, thank you for reminding me. Thank you for asking me in the first place about the linear independence. Okay. There is a definition of linearly independent, and there is a way of finding out if things are linearly independent, and there is a thing that is always true about things that are linearly independent. It's the easiest way to think about them, but isn't the definition. These are all things. So I'm not going to start with the definition, and I'll put it later. Vectors are linearly dependent when any one of them is a linear combination of any of the others. This is the truth. It's not the definition, but it's the truth. So I'm just going to say truth. I guess that's a theorem, probably. That's what truth is in maths. So if you can get a list of vectors and you can look at it and know that one of them is a linear combination of any then it's definitely linearly dependent. So I know, for example, that these three vectors are linearly dependent because this one is that one plus two, is two of that one plus that one. Since 2 of 135 plus 207 is 4617. Now, it's pushing it in an exam where you're feeling stressed out to notice such a thing. Like, I saw at least 3 people go, huh? When I said that. Now, I knew it because I set it up that way. So it's difficult to notice that. But if you do notice such a thing, then you can say they're linearly independent because here is the combination. Sorry, linearly dependent. Yep. I wish they had different words, but this is where we are. So they are linearly dependent because one of them is a linear combination of the others. It doesn't matter which one, it doesn't matter which of the others. It can just even be a linear combination of one of the others, and that would be linearly dependent as well. Yep. I'm going to get there. I just wanted to point out that you can do this. Like, this is a thing you can do. And this will always be true if they are linearly dependent. If they're linearly dependent, it will be possible to write one of them as a linear combination of the others. Not that you care about how to do it, but it is possible. Yep. We'll get to the free variables. Okay. Right. So that is one thing that is true. And to be linearly independent, it must be impossible to write any of them as a linear combination of any of the others. Linearly independent means that this is impossible. One more example of linearly dependent. Any list that includes the 0 vector is guaranteed to be linearly dependent. Because look, this one is 0 times that one. Linear combination. Okay. I'm really sorry that the sound went out. I probably was sitting too far away from the microphone. All right. So, also true. Independent when none are, isn't it? When none of them is a linear combination of any of the others. That's important, okay? So this is harder to tell, right? If they're linearly independent, it can be really hard to tell. But it can be really easy to tell if there's only 2 vectors. Those 2 vectors, I can't make this one as a multiple of that one because this one's got a 0 in that spot, and all the multiples of this one will have a 0 in that spot. And therefore, this can't be a multiple of that either. So with two vectors, it's really easy to tell if they're linearly independent compared to all the other situations you could be in. And the problem is to don't just focus on two vectors. This one, none of them is a multiple of any of the others, but they're still linearly independent because this one's a combination of those two. So one of the things that students can do very easily is to start to think that all they have to do is check if any of them are multiples of each other, and that's not enough to tell they're dependent. Yeah. Because none of these are multiples of each other, but they're still dependent because this one is 2 of that one plus that one. It has to be a proper full linear combination involving both of them to get to the other one. All right. So the definition is this is the definition. If someone asks you to prove that things are linearly independent, that is what the definition is for, proving things. So the definition has been specially chosen so that it's easier to prove. That definition over there makes sense, but it's hard to prove. So the definition of linearly independent is vectors v1 up to vk are linearly independent when the equation x1 v1 plus xn k vk equals the vector 0 has only the unique solution x1 is 0 all the way up to xk is 0. And some people call this the trivial solution. So trivial in ordinary English means unimportant, but it can also mean really easy to think about. That's also another meaning of trivial. And so the easiest solution to think of is that, well, if all the x's are 0, the answer will be 0. That is definitely the truth, and that will always be a solution for this kind of equation for any vectors whatsoever. It's the trivial solution because it's the first one you think of. But if there are any other solutions, then they're linearly dependent. If the only solution is the one where they're all the x's are 0, then they're linearly independent. So the thing is, that's the definition. And that's the thing you would need to use in a proof if you didn't know what the vectors actually were. So if someone just said, prove that some vectors, and they just gave them letters, and you had to prove about linear independence, this is what you would use. But it also tells us how to tell if things are linearly independent without just guessing what the linear combinations are. What it says is, you know what I said about matrices and how if you do way back here, I said that multiplying a matrix by a column vector is the same as doing a linear combination of those columns. Oh look, it's a linear combination of columns. I could do it as matrix multiplication if I wanted. That's the same as saying a matrix made of the vectors v1 up to vk times the vector of x1 up to xk is the 0 vector. And that's the same as making an augmented matrix with v1 up to vk and augmenting 0 on it. And so these become the coefficients of x1 up to xk. And so now, finding out what the solutions for x1 up to xk are is the same as row reducing this matrix. Are these vectors linearly independent? Tricky to tell. I mean, that one's not a multiple of that one. And so those two are independent, but the collection of three of them, not so easy. I don't know, I decide not to guess. And so what I'm going to do is the quickest way to tell is to write them as columns. That's important because of the way that we did this. They have to be written as columns to be able to make this decision. 1, 8, 7, 2, 0, 9, 11, minus 6, and 4. And we can put zeros here. So technically, yep, it does not matter what order you put them in. You will get the same result either way. It might make it easier or less easy to do the row operations if you put them in a different order. Nice to put the one with the 1 in it just here because then I've already got a 1 in the right spot. And so then I will do row operations until I can tell whether there will be a unique solution or not. I don't have to go all the way. Now I'm also going to say that this column here is not going to change no matter what row operations I do. So there's no reason for me to put it in at all if I don't want to. So I'm just going to skip it from this point on. So row 2 is row 2 minus 8 of row 1, and row 3 is row 3 minus 7 of row 1, and this is going to turn to crap. This minus 8 of that is 0, this minus 8 of that is minus 16, this minus 8 of that is minus 94, this minus 7 of that is 0, this minus 7 of that is minus 5, this minus 7 of that is, oh my goodness, minus 73. It's not looking good. Cool. Oh man, really made a hard work for myself. I'm going to swap row 2 and row. You know what? I'm just going to go all out, and I'm going to divide row 2 by 16. So technically you're not supposed to divide it by a number, but it's the same as multiplying it by 1/16, so that's okay. And actually, I really need to multiply it by minus a 16th to make a 1 in that spot. Whatever 94 on 16 is, okay, and then I'll do row 3 is row 3 plus 5 of row 2. That'll put a 0 in this spot. Cool. And that number is not 0 because 16 doesn't go into 5 times 94. And so I'm not going to get a whole number. I'm not going to get a whole number here, and so it's definitely not going to be 0 because 0 is a whole number, so which is not 0. And so now I get a pivot in every column, and so there will be a unique solution, and therefore they're linearly independent. Yay. Yep.
Could you explain that last part again?
Which bit? Which bit am I explaining? Why this isn't 0 or why there's a pivot in every column? Yep. So since this isn't 0, I'll be able to divide it by whatever number it is and make a 1. And then I'll be able to do row operations to make zeros here. and I'll be able to make row operations to make zeros here, and I'll get 1, 0, 0 equals 0, because that's what this was originally. And so my x1 will be 0, and my x2 will be 0, and my x3 will also be 0. And so the only solution is that all of the coefficients are 0, which is the definition of being linearly independent. So we can shortcut the process instead of talking about those coefficients, which I didn't technically mention, and so I'm not really allowed to talk about x1 and x2 and x3 without talking about them. You're allowed to just say, I'll put the vectors as columns and I'll row reduce, and if there's a pivot in every column, then they're linearly independent automatically. So what this definition does is it allows me to do proofs, but it also tells me how to use row operations to make the decision. So if at any point I could tell there was going to be a column with no pivot, then they would be linearly dependent. Yep. And that also tells me that if I have too many columns, it's going to be guaranteed to be linearly dependent because there won't be a pivot in every column, because there won't be enough spaces to put pivots. There'll be too many spaces to put pivots and not enough pivots to put in them. So it's all about there being a pivot in every column. Rows of zeros are irrelevant for this because the only thing over here is zeros, so a row of zeros doesn't matter because a row of zeros is only important if it's not 0 in the answers column. And so since we set it up with zeros in the answers column, the rows of zeros don't tell us anything. Yep. Okay. I'm going to have to stop soon because there's another revision seminar after this. So your question is, when they're linearly independent, does it, if there's two vectors and they're linearly independent, does it span R2? Right. This is the question. The answer to that question is, if the vectors are in R2 and there's two of them and they're independent, then yes, they do span R2. If the vectors are in R3 and they're linearly independent and there's two of them, they don't span R2 because they're not in R2. They're in R3. The thing they span is the same shape as R2, but it's not R2 because R2 is made of things that have two coordinates. So I will just say this. These two vectors are linearly independent and they're in R2 and they're in R2. They will indeed span R2. Every vector in R2 is possible to write as a combination of these two vectors. Something times this plus something times this, I should be able to produce every possible vector with two coordinates. That's what it means to span R2. But these two vectors, they are linearly independent, but they're not in R2, they're in R3. They can't span R2 because they're not in R2. They span a plane in R3. To be in R2, it means to be a vector that has two coordinates. What's that? No, if two vectors are linearly dependent, they will span a line, which is not the whole of anything. It's not the whole of R2 and it's not the whole of R3. Yep. There's only two vectors. You can't span the whole of R3 with only two vectors. That's an important question, right? To be linearly independent, doesn't mean you span everything in the place where you are. If you're in R3, you need at least 3 vectors to span the whole of R3. Whether they're independent, like if they're independent and there's only 2 of them, I can't span the whole of R3. I'll span something, it just won't be the whole of R3. It'll be a plane. I'll be able to get everywhere on that plane, but I won't be able to get anywhere that's not on that plane. Yeah, and so it's a grammar thing. What you want to say is that they span something that's the shape of R2, but you can't say that they span R2 because R2 is made of things with 2 coordinates and these things have 3 coordinates, and so they're not in R2. Yep. Yes, the subspace which is a subspace of R3. The fancy word that they didn't teach you in Maths 1A for being the same shape as R2 is isomorphic. And it literally means same shape. Iso means same and morph means shape. Isomorphic. So,
Just a word. If it is something, it is R2, and if it is
I can't remember what I said. Vectors with 2 coordinates are in R2. Vectors with 3 coordinates are in R3 and cannot be in R2 because they have too many coordinates. I can't draw this vector on an xy plane because it's got 3 coordinates. Which of the coordinates am I going to pick? And so it's not in R2. It has too many coordinates. 1, 0, 0 still has too many coordinates. So you can pretend that R2 is part of R3 by just adding 0 as the 3rd coordinate for everything, if you want, but you're just pretending. The official word for that kind of pretending is embedding. And it's a grammar thing. You just can't say it. Yep. Yep. A line, as long as it contains the origin, is a subspace of any R whatever that it's in. So a line in R2 is a subspace of R2. A line in R3 is a subspace of R3, but it has to go through the origin because a subspace has to have the origin in it. That's one of the rules. But also, it has to contain every linear combination of the vectors that are in it, and 0 vector is always a linear combination of anything you want because it's 0 of this plus 0 of that plus 0 of that. So that's what subspaces are supposed to do. So when you span things, you automatically include the origin because you can do 0 times each of the vectors. That's a perfectly good linear combination. Yeah. So span. Thank you to the people in the Zoom who are helping each other out rather than because I'm forgetting to look at the chat. I appreciate you both. Yeah, span and subspace and all of that take time to talk about to get used to. This experience you're having is normal. That is usual and natural. It takes a while to discuss, to really get a handle on it. That's one of the reasons we have a Maths Learning Centre, not just for subspaces, but there are sometimes it takes, you just have to talk to someone about it. And so if you want to talk more about it, come to the Maths Learning Centre and we can talk about it. Subspace is my favourite bit. But I will say other things are my favourite bit too. So there's a book with little bears in it, you're all my favourites. That's that, you know, I put a meme where they're all like maths topics. So feel free to come and chat about it. Also note that there is revision seminars about subspaces and span and whatever on the Maths Learning Centre website already. The 2014 one is at the top of the list in the subspaces section. It's a really good one. And I talk about all these things, but also you can talk to us about any time. Yep. You're saying a matrix that is a rectangle, not a square, the columns can't be linearly independent? That's what you're saying? This is false because these columns are linearly independent because there is a pivot in both columns. Because it's a narrow matrix, it's possible for the columns to be linearly independent. If it was a wide matrix, then yes, those columns have to be linearly dependent. You are correct. So if it's this way round, is that what you're imagining? That, yes, guaranteed, linearly dependent columns because there's more columns than rows. But if it's this way round, could be either way. Yep.
It's like if you have like X, Y, Z, but you only have two equations to go off. It has to.
Yep. Yeah. The columns have to be dependent. The rows, on the other hand, are independent because there's less rows than there are coordinates in the rows. So in Maths 1B, you will start talking about columns being independent, rows being independent, and find row ways to tell if things are independent as well as column ways to tell. But they hold that off for Maths 1B when you've had a little more time to process things. So you'll do all of the subspace stuff. If you do Maths 1B, you may not, you'll do all the subspace stuff again, but more so. You still have a whole algebra section, a whole calculus section in Maths 1B as well. Yeah, just do more stuff. Not necessarily. So if there are more rows than columns, it's possible for the columns to be independent, but they don't have to be. Because if I had a whole column of zeros, guaranteed dependent, I can always fit a column of zeros anywhere I want. Yeah. All right. Yes. Thanks so much. I really appreciate all of the questions and the discussion. It makes it so much better for me. And yeah, really appreciate it. I'm going to stop the recording now.